Okay, welcome back. So in this lecture, I want to talk a little bit, without too much details, about higher dimensions. And where equivalent 4. Just to give you some historical overview. Historically, the higher dimensional case was in particular studied by the differential geometers Ricci, by Rauch, and Klingenberg. And the methods they used were comparison theorems for geodesics. You've seen some of that, like in Meyer's theorem, the conjugate point. So, in particular, they used properties of the Jacobi equation, Jacobi operator, along geodesics, and analyzed how you can understand the Riemannian manifold on which you pose some initial condition on the sectional curvature. How does it influence the curving of geodesics, and what can you say about the global properties of the Riemannian manifold using just these geodesics? In other words, they were using ODE methods rather than PDE methods. And the most remarkable, the famous result that this theory produced at the time was a theorem, what is known as the quarter-paging theorem of Klingenberg of Berger. And it makes the assumption that, assume that on Mn G with compact, smooth, no boundary, smooth can be replaced, of course, by something like C2. All sectional curvatures satisfy that sigma ij is bigger than 1/4 k less than k for some constant k positive. Then, if the manifold is simply connected, Mn is homeomorphic to Sn. That was the global theorem. Now, there's a strong condition because K is a fixed constant for the whole manifold, a fixed copositive constant for the whole manifold, and on the other hand, the result is only homeomorphic, but you can ask the question whether it may be diffeomorphic. And on the other hand, it's sharp with respect to the 1/4. Note that on CPN, complex projective space, we have sectional curvatures with the standard metric sigma ij equals 1/4 and sigma some other sectional curvature small. So in other words, the result with respect to the 1/4 is definitely sharp. You need a strict inequality either here or there. So then Ricci flow, of course, opened the possibility to have a different approach, like in the 3-dimensional case. Notice that in the 3-dimensional case, before Ricci flow, people didn't even know how to deal and classify manifolds of positive sectional curvature. So Ricci flow even gave a full result, a complete classification in this spirit for manifolds of positive Ricci curvature. So the question is, what can you do for the higher dimensional case with Ricci flow? Now, in Ricci flow, recall that we had an evolution equation for the Riemann curvature tensor. I don't want this lecture to be too technical, so let me just say we had Laplacian Rij KL on the right hand side, and then there was some quadratic term Rij KL depending on the Riemann tensor. And we had, so whether one can prove something with the maximum principle decisively depends on the algebra of this quadratic term. It turns out that you can prove a pinching estimate similar to the 3-manifold case, but with a much stronger restriction initially. So recall that the Riemann tensor could be decomposed into 3 orthogonal pieces. So this was the scalar curvature bit, this was the trace-free Ricci, and this was the Weil tensor. And the Weil tensor was completely trace-free. And the constant curvature matrix that we want in our pinching theorem, as the limit, in our pinching condition, dominates the second and the third term. Recall that because of our general pinching theorem, we just need the pinching estimate on V and W. So we need V squared plus W squared less than the constant times R to the 2 minus delta plus 1 delta. If once we manage this, then we get convergence to a round metric and can prove, for example, Klingenberg's result or other results. So the key will be to prove this. Now, turns out in the Ricci positive case, it can always be done. In higher dimensions, it turns out the first result in this direction is that if initially V squared plus W squared is small compared to R squared, then you can even squeeze in the delta and prove the pinching estimate. Showing the spirit what you can try in higher dimensions, let me mention this result. Long time ago. Theorem 85 for all n greater than 4 there exists some delta n positive such that if on the initial metric we have that the trace-free part of the Ricci tensor and the Weil tensor are small compared to the scalar curvature, and the delta n is given explicitly, Then we get that v squared plus w squared satisfies some constant times r to the 2 minus delta for some other positive delta and the rescaled metric converges to the space form as n over gamma. Now, this is of course a pinching condition in the spirit of Klingenberg, but it's very far, because the delta n is relatively small, this is very far from the quarter pinching condition. It would correspond to a pinching condition for the sectional curvature between 1 and 1 minus delta n, very close to 1. Nevertheless, it's a result which is, on the other hand, better than the Klingenberg result, because it's a scaling invariant condition and it's a pointwise condition. So it's like a pointwise pinching condition where you just need it with a different number k at each point of the manifold rather than with one number k across the whole manifold. Now the proof idea is to compute ddt of the quotient, very similar to the three-dimensional case, but now instead of just taking the traceless Ricci squared, which is enough in the three-dimensional case, you also have to add in the Y tensor squared. And when you first do the computation without putting the scaling breaking delta in here, just to see what happens, and you get the Laplacian of this thing, and then you get something like 2 over r gradient I of the same expression. And then you get a term on the right-hand side. Well, if ddt of curvature is quadratic in curvature, then ddt of curvature squared is cubic. And ddtr we know, so you get here some term, let me put 1 on r cubed, 1 on r, yeah, that's right, r squared, and then you get a cubic term in Riemann. And then from the other term you get a minus v squared plus w squared divided by r cubed times 2 times Ricci squared, which you can combine into some polynomial 1 on r cubed times some polynomial p tilde of Riemann, where the degree of the polynomial p tilde is 4th order. Right? Because here you multiply by r, and here you get a 4th order polynomial in the Riemann tensor. And then the question is, does this polynomial have a sign? So you have now, in particular, this cubic term here is nasty, and the idea is to decompose everything. Decompose all terms, all factors in all terms into u plus v plus w. So for example, here if you have a cubic term, you have 3 factors, and each factor you decompose into 3 terms. That gives you 27 terms. I think there are 2 of them, so 54 terms coming from here, and you have some terms from there. You have about 60 terms. And it turns out they all have, of course, all the terms which have just scalar curvature in them, they cancel. And then you get a sign. So it turns out that there's a technical lemma. If the v squared plus w squared is already small, if you know some of these terms are small, then the p tilde is negative, and you can squeeze in some epsilon depending on this delta n times r squared times v squared plus w squared. And this allows you to sneak in a delta in here, and then apply the maximum principle to v squared plus w squared to the r to the 2 minus delta, and this bad term coming from the delta here can be absorbed in the good term coming from the p tilde on the right hand side. And I spare you the algebraic details involved in analyzing this fourth order polynomial. It's just the purpose is to illustrate that the hard work in the higher dimensional case, trying to prove the pinching estimate, is really algebraic rather than analytic. So let me just report how the story progressed after 85 without claiming completeness. Well, there was then Richard Hamilton, the same year, or maybe half a year later, 86, he proved that if n equals 4, he used the fact that in 4 dimensions the SO4 splits further into SO3 cross SO3, so he could break up the Riemann tensor as a map between 2 forms, the Riemann curvature operator, and in how many 2 forms are there in 4 dimensions? Well, n over 2 is n times n6. Right? So this is a 6-dimensional space. E1 wedge E2, E1 wedge E3, E2 wedge E3, and so on. And you have 6 2-planes in here. And because of this splitting, you can write the Riemann curvature operator as a matrix A, C. In some sense, this is due to the Hodge operator sending 2 forms into the volume form, inserted 2 form, and this gives you this splitting. And you use this algebraic structure to prove that not only does the curvature operator remain positive, can use this to prove the pinching estimate. If the Riemann tensor is positive at t equals 0, as an operator sending 2 forms into two forms. Now, in general, it was known at the time, in fact it was known to Hamilton, I think everybody working on this, maybe the first one to know it was Bourguignon, that ddt of Riemann can be written, this quadratic term on the right hand side can be written as just the square of this operator between two forms and some other term which is also non-negative, where the sharp is a quadratic built from the Riemann tensor as a map between two forms involving the coefficients of the Lie algebra of this space, and both these terms are non-negative operators on the space of two forms, and therefore by the general maximum principle that I explained, positive Riemann curvature operator is preserved. And the question then was, is it true that all manifolds of positive Riemann curvature operator are satisfying our pinching condition and they are therefore diffeomorphic to a spherical spaceform? It was an open problem for many years, and this was then solved by Böhm and Ricci. If the Riemann tensor on the initial metric is positive, then exists the pinching estimate. And therefore, the manifold is diffeomorphic to a spaceform. By our general theorem, once we have the pinching estimate, we know that the Ricci flow converges. And so they proved that positive Riemann is a condition. They had an algebraic idea which basically uses the fact that you use this this decomposition in three terms, but you play with the constants and the way you do it, and optimize alpha and beta, creating certain cones inside the space of curvature tensors. And using these estimates, they were able to prove a pinching estimate, proving this. Now, based on the work of Böhm and Ricci, then later, Brentle and Schön were able to settle the old question of Berger, Rauch, and Klingenberg and replace that old theorem by the optimal theorem, where you just assume pointwise a pinching and quarter pinching, and you get rewarded with a result about diffeomorphisms rather than homomorphisms. So, Brentle chain proved that if the sectional curvature, any ratio of sectional curvatures at each point is between 1/4 and 1 for all p in Mn G0. If you pointwise quarter pinching, then you get the pinching estimate. Then you get the pinching estimate, and therefore you get the result that was open for such a long time, that Mn is diffeomorphic to Sn by some group of isometries. optimizing the old theorem of Rauch, Berger, Klingenberg. I should also mention that Brent extended, not extended, it's not the right word, extended this result by using a condition that was brought up by Mikhailov and Moore. And this condition is positive isotropic curvature. And it was first introduced by Mikhailov and Moore in the case n equals 4 and 4 manifolds, where they related it to the existence of harmonic two spheres and the 4 manifold, and showed that this positive isotropic curvature is exactly coming up in the stability of minimal surfaces or harmonic maps into a 4 manifold. And the positive isotropic curvature is, the condition says that you have a positive isotropic curvature if in any 4-dimensional frame, in any 4 frame, E1, E2, E3, E4, contained in the tangent space manifold, you have that R1, 2, 1, 2 plus R1, 4, 1, 4 plus R2, 3, 2, 3 plus R2, 4, 2, 4 minus 2 R1, 2, 3, 4, that this is positive. Then you call this manifold of positive isotropic curvature. And the name, of course, doesn't come from this condition. This condition is equivalent to a natural condition on the complexified tangent bundle. So to complexify the tangent bundle, the vector spaces, you complexify the metric, make it into a complexified bilinear form, complexify the Riemann tensor, and then there are the so-called isotropic directions. And if you insert 2 isotropic directions into the Riemann tensor, then you want those directions to have non-negative curvature, and translate it back into the real setting. This comes up with this condition. And it was shown that this is a good condition that is preserved by Ricci flow. And Brendle used this condition to prove theorems, and I should also mention that there were results by this direction by Andrews, Ben Andrews, and his student Nguyen, and then by Nguyen himself in this direction. You should look at the book. See, book by Simon Brendle, where this story is spelled out in great detail. And the computations are quite involved and very algebraic in nature, so I will not go into the details here. Okay, now this is how far you can get in high dimensions so far if you want to get a solution that satisfies a pinching estimate and converges to a spherical space form. That's all there is known in this direction. Now, if you relax the curvature conditions in higher dimensions beyond what I just explained, then you anticipate singularities, different singularities than these nice uniformly shrinking spherical singularities. And that's a completely different story that we deal with later on in the course. The one thing that still remains now is the two-dimensional case. We didn't talk about the two-dimensional case at all. So let me mention the two-dimensional case. So suppose M2 G0 is a smooth Riemannian, well, two-manifold. This traditionally is called the Riemann surface. Again, let's assume it's compact, no boundary, closed, Riemannian surface. And now there's a lot known. In particular, there's the famous uniformization theorem. So the uniformization theorem says that if we are in the orientable case, if M2 is orientable, then G0 is conformal to a metric of constant Gauss curvature. And it's well known how large the space of conformal metrics is, and depending on the genus, and it's known that the topology is completely classified by the genus of the surface. And twos classified topologically by the genus. Question is, can you prove all that with the Ricci flow? Make Ricci flow approach to this. Now, Richard Hamilton told me at the time, in the mid-80s, that if he had known how difficult the two-dimensional case is, he may have never tried the three-dimensional case. And the reason that the two-dimensional case is completely covered by the uniformization theorem meant he was not interested in the two-dimensional case at first, and he went straight for the three-dimensional case. Because the two-dimensional case is not at all easy. Let's see what happens in the two-dimensional case. So if n equals 2, then the evolution equation ddt of gij is equal to minus 2 times rij, because the Ricci tensor now takes the form in diagonal coordinates. We have just g times where g is the Gauss curvature. So we have that the Ricci tensor is just g times capital G times gij, and the scalar curvature is the trace So the scalar curvature is twice the Gauss curvature in the two-dimensional case. So our evolution equation for the Ricci tensor, for the metric, is just this one. And minus 2 times, so this is equal to minus r times g. Okay. And so, but this is just a factor in front of the metric dependent on space. So this is a conformal deformation in the same conformal class. So solutions are always in the same conformal class. Okay. If you start in one conformal class, you can never leave it with Ricci flow because we always just multiply the metric with a function. The second observation is that now the evolution equations for the Riemann tensor become very simple. Right? Because we know what ddt of the scalar curvature is, so we have ddt of this. Let's deal with the scalar curvature, otherwise you have always a half floating around. So our old evolution equation was that this is equal to Laplace r plus twice the Ricci curvature squared. So in this case, the Ricci tensor squared is g squared plus g squared. So it's 2g squared, so we get 4g squared. But 4g squared is just r squared. So we get Laplace r plus r squared in this symbol. And the rescaled equation in the two-dimensional case also takes a very simple form. So we get the rescaled equation where the metric g tilde is psi of t times g of t, and the tilde dd t of the volume of g tilde of t is identically 0. To fix the volume is given by, well, we had to put dd g tilde ij is equal to minus r tilde g tilde ij, and then we had this term 2 over n, which is 1, times r tilde times g tilde ij, where r tilde is equal to the mean value of the scalar curvature. But this volume is constant, and by Gauss-Bonnet this is constant as well, which is a constant which just depends on the genus of the Riemann surface. So, for example, on the torus, this term would simply be 0, whereas on the sphere, this would just be for pi. So the evolution equation in the two-dimensional case is very simple. We can also write it as, you see that this is again conformal, of course, that this is just r tilde minus r tilde capital times g tilde j. And of course, the metric where the Gauss curvature or the scalar curvature is equal to a constant, these are the stationary points of this flow. And these are the solutions of the uniformization theorem. So it is reasonable to hope that the solution of Ricci flow in this case converges to a solution of the constant Gauss curvature equation. And indeed, this result turns out to be true. It was shown by Richard Hamilton. And there's a special case that was settled. One special case on the two-sphere was settled by Ben Shah. But the result is, the spirit comes from Richard Hamilton, and the result said that you can indeed prove the uniformization theorem. So for any Riemann surface M2 G0, the solution of Ricci flow in the rescaled version converges smoothly, actually exponentially fast, to a metric of constant Gauss curvature. And now the proof will be requiring new ideas, and it will be a little bit involved if you are not using the uniformization theorem at all. If you're willing to use that you already know the uniformization theorem, then the proof, the last part of the proof, will be slightly simpler. But the main new ideas that come in here are independent of whether you want to use the uniformization theorem at the end or make the proof completely independent. And these new techniques I want to focus on in the next lecture. These new techniques are relevant not just for the two-dimensional case, but will turn out to be crucial also in the high-dimensional case if we don't restrict ourselves to the positive curvature setting. Okay, thank you.